In this video, we're going to talk about taking all of that information that we were pulling from rational functions in part one and putting that together in a graph of a rational function. So I'm going to start with the basic shape of a rational function. You're a little bit familiar with that from our transformation section, at least with the basic shape of a rational function with one vertical asymptote. So if we start with that, if you remember from that previous section, that if I have a rational function and I'm just going to make the horizontal asymptote be at y equal to 0, and let's just say I have a single vertical asymptote here, then the basic shape is that I have a branch in two of the quadrants that are created by those vertical and horizontal asymptotes. So I may have a branch here, and then I may have a branch over here. But keep in mind, the branches don't have to be in the first and third quadrant. I could have branches that are in the second and fourth quadrant, or I could even have a branch that's in the first quadrant and one that's next to it in the second quadrant. So those branches could be in diagonal quadrants from each other, or they could be next to each other. They just can't be on top of one another, otherwise it would fail the vertical line test. Now, what we haven't talked about before was what the basic shape would look like if I had two vertical asymptotes. So again, I'm just going to make the horizontal be at 0, but now I'm going to make up just two vertical asymptotes to look at. So on the outside of the vertical asymptote, so what I mean by that is on the left side over here and the right side over there, the branches that you saw in the shape with one vertical asymptote are where those branches appear when I have two vertical asymptotes. So in other words, I could have a branch here and then a branch diagonal from it way over here, or they could be both above the horizontal asymptote or both below, or diagonally in the second and fourth quadrants. But that's where the branches are. What changes with two vertical asymptotes is what happens in between the two vertical asymptotes. So what can happen in between is I can have a shape that either looks like a cubic function or a shape that looks like a parabolic function. So if I have a shape that looks like a parabolic function, it just looks like I have a part of a parabola inside those two vertical asymptotes. And that parabola, that parabolic shape, can either open up or it could open down. So we'll have to figure out that as we go through our graphing. And then just real quickly, if I have two vertical asymptotes, one other shape that I can have in the middle is something that looks like a cubic function. So I could have on the outside, I have those branches, and then in the middle, I could have a shape that looks like this. And again, that shape could be reflected over the y-axis, so that shape could also be turned this way. And again, we'll figure that out as we go through the graph. So I want to move now to an example of a rational function where we're going to find all of the information, and then we're also going to graph it. And this first example is going to be an example with a single vertical asymptote, and then we'll take a look at a couple of examples where we have two vertical asymptotes. So remember from the previous one that we worked on finding all of this information. So I'm going to go through this maybe a little bit quicker just because you will have already had practice with that. The new part to this is the graphing of it. So we start with the domain, and remember for the domain we want to set the denominator not equal to 0. So for this one, my domain is x cannot equal -2 and x cannot equal 2. Now, if we move to the wholes, Remember, I want to look for a common factor in the numerator and the denominator, and I see x minus 2 is a common factor. So x minus 2, set that equal to 0 and solve for x. And I have a whole located at 2 comma something. So we're going to use the simplified version of the function to find the y value of that whole and everything else in my list. So I'm going to rewrite this function after dividing out that x minus 2. So if those x minus 2's divide out, I'm left with x plus 1 over x plus 2. So now I can plug that 2 into that simplified version of the function to get the y value for where the whole will occur in the graph. And I get a y value of 3/4. Now for the vertical asymptote. For the vertical asymptote, I want to set the denominator of that simplified version of the function equal to 0. And I get a vertical asymptote of x equal to -2. For the horizontal asymptote, I want to identify the leading term, so the term with x of the highest degree, to the term with the highest degree in the denominator, so that would be x over x. And I want to reduce that since the number of x's is the same in the numerator and the denominator. I just want to reduce this. Remember, there's ones in front of that, so x over x equals 1. And when all the x's divide out, then whatever remains, whatever that simplifies to, is my horizontal asymptote. So I have a horizontal asymptote at y equal to 1. For my x-intercept, remember we talked about the little shortcut in setting this function equal to 0, that I just need to set that numerator equal to 0 of the simplified version of the function. So I've got an x-intercept at -1, 0. And finally, for my y-intercept, I want to plug 0 everywhere I see an x. And again, for this, I'm going to use that simplified version. So 0 plus 1 over 0 plus 2 gives me a y-intercept of 0, 1/2. Okay, so there's all the information that I'm going to use to sketch the graph of the function. So what I need to do now is start with plotting my points that I already know and draw in the asymptotes, and then I'm going to find a few more points to plot. So I know that I have a vertical asymptote at -2, so I'm going to draw that dotted line. And I have a horizontal asymptote at y equal to 1, so I'm going to draw in that horizontal asymptote. Now, what I want to do is plot any holes and intercepts that I already know. So I know that there is a hole or an open point located at 2, 3/4. So I'm going to go over to 2 and up to 3/4, and I'm going to just draw an open point. I also know that I have an x-intercept at -1, 0, so I'm going to plot that point. And I also have a y-intercept at 0, 1/2, which would be right about there. So now, because we have we have one single vertical asymptote, remember what that means is that I have two branches, one on the left and one on the right. So when you're looking at the right side of this vertical asymptote, it's kind of obvious whether that branch is above the horizontal dotted line, the horizontal asymptote, or below. So because I already have points plotted here below the horizontal asymptote, I know that the branch has to be down here. So I'm going to draw the branch, and remember to leave that open point a hole in the graph, so don't draw your line through it. I just want to come up to that open point and then continue on the other side of that open point. So I know that that branch is there. So what I want to do is figure out where I should draw the branch on the left-hand side. So to figure out where we're going to draw the branch on the left-hand side of the vertical asymptote, what we need to do is plot a point on that side. So on the right-hand side, we had all of these other points that we could go off of to figure out where the branch is. But on this side of the vertical asymptote, we don't have any points, so we need to plot one. So remember, this vertical asymptote is at x equal to -2, so let's pick an x value on this side of that vertical asymptote. Let's pick -3. So what I want to do is figure out where that point would be plotted if I let x equal -3. So remember, I'm going to just plug that into the simplified version of my function. So if I let x equal -3, I've got -3 plus 1 over -3 plus 2, which is -2 over -1, or 2. So if I plot -3, 2, now I know where the branch on that left-hand side goes. Because if one point is in a quadrant, then all the points on that side are in that quadrant. So by plotting that one point there, I know that this branch is going to be in that quadrant of the vertical and horizontal asymptotes. So if you already have points plotted, you can determine where the branch goes. But if you don't, then you just might have to plot one point to figure out where that branch should go. Okay, so let's move now to an example where I have two vertical asymptotes and take a look at how that works. So we're going to start through finding all that information again. So the domain, I look at my denominator, and x cannot be -3 and x cannot be 2. For the holes, I do not see from top to bottom that there are any common factors with the numerator and the denominator. So that means there are no holes in the graph at all. And for the vertical asymptote, those are going to come just from the denominator. So if I set those factors in the denominator equal to 0, I'm going to get a vertical asymptote at -3 and a vertical asymptote at 2. For the horizontal asymptote, I want to compare leading term top and bottom. So on top, my leading term is x. In the denominator, I want to picture what this would be multiplied out, what it would look like multiplied out, and my leading term in the denominator would be x squared. And if I have more x's in the denominator than I do the numerator, then my horizontal asymptote is y equal to 0. For the x-intercept, I want to set my numerator equal to 0, and if I do that, I get an x-intercept of 0, 0. And for my y-intercept, if I put in 0 everywhere I see an x, I'm going to have 0 over -6, which is just 0. So my y-intercept is also 0, 0. So let's start taking a look at the graph. So just like before, the first thing I want to do are my asymptotes. And this time my horizontal asymptote is y equal to 0. So I'm just going to dot the ends of my x-axis to show that. And the vertical asymptote is located at -3. And also I have a vertical asymptote at 2. Now the next thing I want to do are plot any points. So there are no holes, but I do have an x and a y-intercept both located at 0, 0. So the fact that I only have that one point is kind of not the best thing for me, because that means I've got a lot of points I need to find in order to figure out where all of my branches and where my pieces of my graph in between the asymptotes are. So let's just start left and work our way right. So what I mean by that is I need to figure out where my branch is on the left side of that vertical asymptote. So remember, this vertical asymptote was at -3, which means that I need to pick an x value somewhere over here to the left of -3. So what I'll choose is -4. You can pick anything you want to the left of that vertical asymptote. So if I do that, what I'm going to do is plug that -4 back into this original function. So that's going to give me -4 over -4 plus 3 is -1. -4 minus 2 is -6. So I get -4 over 6, or -2/3. Now, I don't really have care about where I'm going to plot this. All I wanted to figure out is on this side of that vertical asymptote, am I above the x-axis or below the x-axis? And because my y value is negative, that tells me that that branch has to be on the bottom of that horizontal asymptote, or below my x-intercept. You can literally plot it. You can plot -4 and then estimate where -2/3 is. But that test point is really just to figure out where the branch should go. Okay, moving on down the line from left to right, the next place that I have to test is in between this vertical asymptote and where this point is. So I want to test in between -3 and 0. So I need to pick a number, because remember, in the middle there, I could have a part of the graph that's above and a part of the graph that's below, depending on the shape that's between those vertical asymptotes. So I'm going to pick a number in between -3 and 0. So I'm going to pick x equal to -1. So plugging that back into the original function, I have -1 over, so in that first factor, -1 plus 3 is 2, -1 minus 2 is -3, so I get -1 over -6, or +1/6. So if I were to plot -1, 1/6, that means that from this vertical asymptote to that point, my curve is above the x-axis. So now we need to figure out if that graph turns around and goes back up, or if it continues to continue down below the x-axis. So that moves us to the next test point. So for my next test point, I need to test in between these two. So I need to test between 0 and that vertical asymptote of 2. So if I do that, I'm going to test x equal to 1. And if I plug that into the original function, I'm going to have 1 over, 1 plus 3 is 4, 1 minus 2 is -1. I'm going to end up with a y value of -1/4. So if I plot 1, -1/4, that's going to be below the x-axis. So that means my graph continues on down below the x-axis. All I need is that one point to tell me where to draw my branch. So we've got one more area to test, and that is to the right of this vertical asymptote. So this vertical asymptote was at 2, so we need something to the right of 2. So I'll pick x equal to 3. And if I plug that into the original function, I'm going to get 3 over, 3 plus 3 is 6, 3 minus 2 is 1, so I'm going to get 3 over 6, which is +1/2. So if I plot 3 1/2, it tells me that the branch on that side is above the x-axis. And there is the graph of that function. That's probably the worst case scenario, where I had to literally test a point in every single interval to figure out where the branches are. But If you can do one like this, then I don't see any that you're not going to be able to work your way through. So I'm going to stop this video right now because it's getting kind of long. There is one more example there in your notes. So I would like for you to try that problem, and then I'll do another video separate from this one that shows the answer to this so that you can check your own work.